Recording in progress.
Yeah, comes on everyone. Let's start off. Great. So last thing that we did was a robo now. Rough pulley. Okay, let's go ahead with this. Let's see a question on this before going ahead on what we learned last time. Let's say we got a rod here. This is fixed. This whole rod is rotating with omega. There's a person A here. There is a person B here. Let this be L and let this be R. So A is going in a smaller circle. B is going in a bigger circle. Find velocity and acceleration of B with respect to A. Find the centrifugal force and pseudo force on B as seen by A. Mass of A is Ma, mass of B is Mb. Okay, let's get this. Again, let's see. So the first was straightforward. If you ask observer A, what is B doing? He will say he's always in front of me. Observer A feels B is at rest. There is nothing there with respect to him. So therefore, velocity of B with respect to A is 0. Acceleration of B with respect to A is 0. If they ask you relative velocity, it is directly 0. Last time we discussed why. You cannot directly do VB minus VA. That's only the translational relative velocity. Because this person head is also rotating, that will give you a rotational translation velocity, rotational relative velocity. Next thing, what is centrifugal force ka definition? So the centrifugal force is mass of the body which you're observing, mb, right, into omega square, and the distance between the two people. So that is r minus l, right? And this will be outward. So when you ask A to get the centrifugal force, this is what he will write. So A will say the distance between me and the body is r minus l. So the centrifugal force is mb omega square r minus l. This is your centrifugal force. And A will also say, I myself have an acceleration, which is omega square L. This is your acceleration, because of which you get one more pseudo force, the linear pseudo force. This is what you studied in NLM, which is mass of the object into acceleration of the observer in the reverse direction. So that is minus acceleration of A. So that would be m omega square L. Now, the total pseudo force would be the combination of these two. The total pseudo force, when you add this will be mb omega square r minus L plus mb omega square L. The L will cancel out. You end up with mb omega square r. So that's the difference there. Now, if I had kept one more person here, let's say center C, if you ask him to solve the problem, you know what he will say? He will say, okay, there's a centrifugal force, m omega square r. My acceleration is 0. I'm not going anywhere. So there is no linear pseudo force. So this is the centrifugal force and this is the pseudo force. Now, if you observe, the pseudo force in all frames will be same. So don't get confused with that. Pseudo force actually has 4 components. In that, linear pseudo force is 1. There are 4 components: linear pseudo force, centrifugal force. These two we'll see later on. So it doesn't matter where you stand. This net pseudo force will be same. That is just for understanding. But remember, whenever we do problems, where do we keep the observer? At the center. C is always the observer. That's it. Don't unnecessarily make it complicated and confused. For solving problems, keep the observer at the center. Your life is simple. Yeah, but they might ask theoretical questions like this. So just in case. Clear with this. Next time. Let's see. One more theoretical thing. Let's say we got a wedge like this. The wedge itself is going with V1. Inside the wedge, we have a ball which is going with V2. And this is the R there. A ball of mass M moves inside a circular cavity of a moving wedge. As shown. V1 and V2 are velocities in the ground frame. Find the normal reaction on the ball. Let's get that. Let's see. So the important question comes is step one, draw the free body diagram. Now, before drawing the free body diagram, let me ask you this. Is this particle going in a circle? Is this particle going in a circle? So the question comes, who is asking? Who is asking this question? Is the guy on the ground asking? If you say the person on the ground will not think this is going in a circle, this must be going in some weird way. But if you ask this guy on the wedge, he will say, so because there are two things happening. Every time it goes here and the wedge is going this way, this guy is definitely not going in a circle in the ground frame. That's an important thing. So if you want to use centrifugal force, you need to stand in a frame where you're rotating. So my observer is standing at the center here. So my observer is standing at the center of the circle. He himself is going with V1. He thinks it is going in a circle. And he will think this velocity is V2 minus V1, or V2 plus V1. So velocity of the ball with respect to the center is V2 plus V1. So this is an important thing. So when you write centripetal acceleration, when you write the formula V square, that V is not the velocity in the ground frame, it is a relative velocity. V relative square by R. So here V relative is the velocity of the ball with respect to the center. So now when you draw the free body diagram, you will write normal reaction, mg. You can say, I can use this acceleration, or I can say centrifugal force, which is m v1 plus v2 whole square by r. Yeah, done. So we get n is equal to mg. So be careful with that. Don't write mv2 square by r. And remember, this question will again come in momentum. Clear? Not a big deal, but yeah, that is a catch there. You should get the velocity of the ball with respect to the center, but the center itself is moving. Okay? Yeah, most of you did get it. Let's see one more. So we got a system like this. So we got a rod here and we got a spring here. So this is a ring which can slide on the rod AB. This is AB here. This is length L. This is also length L. This here is a spring. And this whole setup here is rotating with omega. So if I show you this is the top view, this is how it looks. This is O, this is B, this is A. So the spring, right, is connected to B, it is fixed here. And there is a spring like this, and this is the particle mass M. This whole setup is rotating with omega. Initially, the spring is a natural length. So once you start rotating this, the spring will start stretching and it reaches equilibrium. Okay, is the spring constant? So spring is fixed at B. The other end is attached to the mass. Find the elongation of the spring in equilibrium. And this was I think this was a PYQ. Not a tough question, means one, but a standard one. Let's give it a try. Let's see. So now when this thing stretches, this was length L. This will become L plus X. Now, if you look at the forces here, the centrifugal force again, my observer is standing at the center. The centrifugal force will be away from the center, which is, let this distance be R. M omega square small r. The centrifugal force will be this way. Let this angle be theta and let this be angle theta. So the centrifugal force component will be m omega square r cos theta. This is 90 degrees here. Hope that was clear. So this was 90. If this was theta, this was theta, right? And so if I look at the top view, this is how the picture looks, everyone. This was O, this was B, and this was A. So A was actually going in a circle of this. Something like this. This is the centrifugal force m omega square r. The spring force will be in this direction, kx. When you took this as theta, this was m omega square r cos theta. This distance was r, this was L, and this was L plus x. The picture is important. The question is pretty straightforward to solve. So since it is an equilibrium, m omega square r cos theta is equal to kx, but r cos theta is nothing but L plus x. Take out x common from here. You end up with m omega square L by m omega square k minus m omega square. There. Clear with that? The centrifugal force will act away from the center, whereas the spring force will act along the rod AB. And the spring force is along AB. Everyone clear with this? It is more true with the picture than actually solving there. Next thing. We will do a part of this question. Later on, we will see the full question later on. So uh, there is a groove like this. So if you look at the top view, we got a disk. So there is a groove like this. Someone made a gap here and you kept a block here. Initially, the distance is r by 2. And this whole setup is rotating with omega. The whole thing is smooth. To find the speed of this block when it comes out of the rotating disk. This omega is constant. And the radius of the thing is r. Let's see. Again, let's keep our observer at the center. So if you ask him to draw the free body diagram, he will say, okay, when the block is here at a distance x, according to him, the centrifugal force is dragging it out, m omega square x, and we get an acceleration A here. So we get m omega square x is equal to ma. So we get acceleration is equal to omega square x. Again, be careful. What is this? This is the acceleration as seen by this observer. When you integrate this, you get v dv by dx. Limits will go from r by 2 to r and 0 to v. We get v square by 2 is equal to omega square x square by 2. Limits will go from r by 2 to r. That would be r square minus r square by 4. So we get v is equal to root 3 r omega by 2. But again, be careful. This is the velocity with respect to the observer. In this case, which you see, this is the radial velocity. He thinks it is going away from the center. But if you actually see this in the ground frame, so that means when this block is coming out, what we calculated was this velocity, v radial, which was root 3 r omega by 2. But there is also a v tangential because you are rotating with the disk. The moment you come out, there's also an r omega there. So this guy is not going to come out straight. It will actually come out at an angle. So that speed will be root over square. This thing will get root 7 r omega by 2. So if you actually try to draw the path of this, initially the block was here. This block is actually spiraling out. The person on the ground frame will think this is how it is traveling. Then gone like this. That's what we will see. Spiraling out. So there are two velocities here. The one, the radial thing, and the v tangential thing. So basically the observer head is rotating, we ignore that. So he thinks it is just going straight out, but there's also a tangential component. So be careful with that. If you just write root 3 r omega by 2, that will be wrong. Because when they say find the speed and they don't mention anything, it is always in the ground frame. Clear with this? That's one thing there. Next thing, banking of routes. This is a concept. This is also a question. This is also there in your, if you're doing HSC board, then it is there in your 12th. Banking of routes. So what is this banking of roads? Meaning, if you ever been on a curved road, when you go on Mumbai Pune Expressway, that part, you must have observed this. Whenever there's a curve, the roads are not exactly flat. So the curved sections of the road are constructed at an angle theta with the horizontal. Now we need to see why they do that. When I was in school, right, I used to own a cycle. So there used to be a part of road like this curved. I used to think, maybe it is to collect the rainwater. So whenever it rains, so the water will go away. So you start making up your own theories. So this is called banking of roads. And the angle is called banking angle. So if you're into civil engineering tomorrow, you will need to know this stuff. So if you are constructing a road, there are a lot of things you have to take care. So let's see the cases, okay? Case 1, we have a rough horizontal road. So you didn't bank the road. So there is a road, there is a curve, and you just made it flat. See what happens. So we have the road, top view. Now, whenever the car goes in a circle, we know there should be a centripetal acceleration. And it has to be provided by someone. And that someone is nothing but friction. There is no one else. Since you are going in a circle, there will be a centripetal acceleration AC is equal to V square by R. So then we write friction is equal to mass into V square by R, but we know friction ka value is less than equal to mu mg. That means we get V is equal to root over mu rg. You actually got a speed limit. So the meaning of this thing is up to this speed, the vehicle won't slip. And this is a problem. The reason why this is a problem, the mu, it depends on the condition of the road. Imagine you're going in the morning when it is sunny, right? Evening when you're coming, it started raining. Because of the water, road becomes little less rough. You start slipping. So morning when you went on 40 kilometers per hour, nothing happened, but evening it started slipping. You brought a new car, the tires have good grip, vehicle doesn't slip. After 6 months, your tires become little smooth, your vehicle slips. Can you see the problem there? The road, when it is initially laid, it is good. After 1 year, the road becomes smooth, vehicle slip. This especially happens, so if you don't do banking, you're completely depending on mu to make sure you to go in a circle. So mu depends on the condition of the road and the vehicle. Meaning you don't know at what speed the vehicle should go anymore. So as a civil engineer who built a road, you have done a disaster, which BMC does a lot. So this especially red happens on flyovers. I think last year they had a flyover somewhere near Kurla or something. They built it. It is generally difficult to put banking on flyovers, but yeah, they could have done something. So the flyover was opened. Four-wheelers generally don't have a problem, but these two-wheelers, right? On the first day, I think almost 120, 130 two-wheelers fell down on that highway. People were just slipping, just randomly. There's a curve, people are slipping. There's a curve, people are slipping. I think it happened in 2 to 3 days. They shut down the whole road and they had to again do some stuff on it. So this is a problem. So you are completely depending on friction mu, on which you don't have any control of your own. So this is a very bad road. So case 2, let's say the road is smooth. We will go to the case 3 when it is rough also. Smooth, but the road is banked. This is how the picture will look like. If you ever seen this, F1 racing car ka tracks and all, they kind of look like this. This is a NASCAR ka track. This thing has a banking angle of 31 degrees. So when you construct the road, so this is how you construct it, the side view. So the road is slightly elevated on one side. Normal roads have a banking angle of like 7 to 10, 12 degrees. Even trains have banking angle, but that's only 1 to 2 degrees. Yeah, this racing car, they do have a lot, so they need a huge banking angle. So how does this work? Same thing. Let's draw a free body diagram and see what happens. So if you draw the free body diagram, and let's say if this is the vehicle, this guy is going in a circle. Let's see the forces. You have your mg, you have your normal reaction. There's no friction because I've taken it to be smooth, and there is an acceleration AC, which is v square by r. Now, if you resolve this into components, this would be 90 minus theta. So horizontal component will be n sine theta. The vertical component will be n cos theta. So we can clearly see the normal reaction is providing the required centripetal acceleration. So n sine theta is providing mv square by r. N cos theta is balancing your weight. If you divide them, you end up with tan theta is equal to v square by rg. This is called the banking angle. And the v is called root over rg tan theta, meaning even if there is no friction, if you go with this speed, you're safe. This is called the banking speed. So you built a road on which you can comfortably say, you can actually put a signboard and say, if you go with this speed, you will be safe. And the best part about this thing, it doesn't matter whether the road is smooth, whether it is raining, not raining, old car, new car, whether it is a car or a cycle or a lorry, independent of mass. Now on top of it, if you have friction, now you get a bonus. The friction becomes your additional. There's something it starts slipping. No, if you're going in a straight line, there is no slipping. That is because if you're applying brake suddenly, you'll slip and all. That has nothing to do with this. If you're going in a straight line, nothing happens because of this. The case 3. The case 3 is the question plus theory. Rough banked road. So the road is also banked and you also rough. Now friction becomes a secondary thing. So even though it is written the speed limit is 40 kilometers per hour, even if you go 50 kilometers per hour, you're still safe. So the friction will provide that extra balance there. Now it becomes your backup. Now here we have two cases. Let's say you're going really fast. Now if you're going maximum speed, the vehicle has a tendency to slide outside. So the forces will be I'll just resolve this into components. So let's say this is a normal reaction. Mg sine theta, mg cos theta. Friction will be this way. F max, because you're trying to go outside, F max will be this way. Since you're going in a circle, there'll be also a centrifugal force, m omega square r. The whose component will be m omega square r cos theta, m omega square r sine theta. We need to resolve the centrifugal force components also. Now, when you write these equations, we get normal reaction will be mg cos theta plus m omega square r sine theta. So your normal reaction increases. And in this direction, mg sine theta plus F max is equal to the centrifugal force. So the centrifugal force is trying to drag you out. This would be mg sine theta plus, we are using omega, na? Let's use v square by r. We're trying to find speed anyway. Then it is mu into mg cos theta, it's lengthy. Yeah, I can do it in omega and then I can substitute it, but bring everything to one side. Remember, this will be the maximum speed. If you exceed this, you're going to skid. M will cancel everywhere. Then This would be g into sine theta plus mu cos theta. R will come here divided by cos theta minus mu sine theta. Correct. Check. That's your maximum speed with if the road is banked and you have a friction. In the exam, they can ask you this. What is the condition so that the car never slips? The meaning of that statement meaning, even if you go with infinite speed, you should not slip. So the condition for no slipping, Vmax must become infinity. That's the meaning of it doesn't slip ever. So if Vmax tends to infinity, the denominator will become 0. The cos theta minus mu sine theta must be less than 0. Then we get tan theta. Tan theta, mu should be greater than cot theta. If you satisfy this condition, greater than or less than, less than, wait, I think mu sine theta, cot theta must be less than equal to mu. So if you satisfy this condition, the vehicle will never skid. Clear with this? What is the minimum speed? If you go too slow, what will happen? The car will try to slide downward. Then you get a minimum speed. Then in that case, friction will be upward. Can you do that? I'll give you a minute. Find the minimum speed. So maximum speed, you're trying to go out. Minimum speed, it will try to go down. So Fmax will be up. That's the only thing will change. All the equations will look identical. Give it a try. Did we do angle of repose? I didn't teach you yet. I'm going to do it today. Yeah. Bits and pieces of theory there. Angle of repose, we did it in friction. No? We don't need it here. Banking angle. It's confused. Get this, get this. It's regular stuff. There's nothing there. Keep doing. This would be for the minimum speed. This will be tending downward. So the only thing I need to change is F max here. Then normal reaction will remain same. Mg sine theta. This will become minus F max. This will become minus. This will become minimum, and this will become minus here, and this will become plus here. Check. That will be a minimum speed. And again, same thing for V minimum to be 0. Now think about it. You're going on a car and for some reason you stopped it on the road. You don't want the vehicle to slip. So for V minimum to be 0, we get sine theta. The numerator must be 0. This will give you the angle of repose. So even if you stop the vehicle on a banked road, you don't want it to slide downward. There. So your answer, right? So if you have a banked road, you can go up to maximum and minimum. Generally, when they construct the roads, they make sure V minimum is 0. If you're building a race car, like NASCAR or F1 racing thing, we will make sure their Vmax is infinity. Because in a racing track, the faster you go, I want the cars to be safe there. There, it's okay. The speed limit can be, it's okay, 20, 30. Cars do go with that speed. But the problem is if they go faster than they fly off into the stadium, that's a bigger problem. So that's why if you see these angles are quite steep. Here you make sure the Vmax is infinity. Normal roads, you make sure V minimum is 0. All clear with this? That's a little about banking. So like these are the 3 cases. So smooth road, rough road, and the banked road. So that's the reason next time when you see a curved road, this is the reason. It is not for rainwater. That's what I thought for years. I think after 11th standard, I realized like when you're a kid, you can do a lot of stupid things. Look at this.
Objective: to understand the role of friction at circular turnings and banked roads. That when a car takes a turn, each curvilinear section.
So this is what he's showing as it's a horizontal road, flat. There's no banking, but it is a curved road.
Can be approximated to be an arc of a circle with equal force.
So it's going in a circle.
Friction.
You can see there are 4 frictions on the 4 tires. You can treat them as one big friction.
The surface the car is moving on. The normal force
reaction
balances the weight of the car mg.
Same stuff. F is equal to mv square by r. Everything that we derived.
With such that it satisfies.
I hope you're getting. Look at the road there. This is a flat road, but it is curved. Don't get confused between both of them. This is not banked.
The relation less than or equal to
you get v less than mu rg.
If the car moves with a velocity greater than
if you go faster than this, the car will start. Can you see how it is skidding out? Now look at it. Now it is raining. Now see, when the road is straight, there's no problem. When this car tries to take a turn, and if it is raining, you didn't bank the road must have become smooth.
Banking of roads. We cannot always rely on friction, as it depends on external factors such as rain or.
This is what happens. You'll start skidding. Not a good thing.
Cost significantly decreases the value of static friction. To avoid skidding,
so we bank the road.
Outer edge of the road is raised up, which is.
This is a little, too much raised, but there you can see.
Suppose surface.
That's how you bank the road. Like, this is an extreme case. Exaggerating figure. And then he's going to do all the calculations we did. But this is for a smooth banked road.
Radius of curvature would ensure that the vehicle remains in its designated path.
And the best thing about this, it doesn't depend on mass.
This is known as speed of a turn.
It can be a truck.
Rated speeds of the object.
So it works.
Summary.
Clear with the banking of roads? Next thing. So this is a story I heard in Europe, right? I don't know when is this exactly, but some company, right? Some civil construction company, they got a contract to build a racetrack. After building the racetrack and during testing, they realized something. No matter how fast you go, all the cars take same time to complete the trip. That is such a hopeless racetrack, isn't it? That means no one is going to win. So something like that happened, and later on they had to do the whole renovation and they had to change whole track and all. I read it in some article. So let's say you made a curve like this. So you got a bowl here, y, and this is your x coordinate. So This is the origin. So this is a marble racetrack. So smooth marble racetrack. So the game is this. You and I will take two marbles and we'll throw into this. Whoever will complete the revolution first, they win. Beyblade wala, if you've ever seen that. So smooth marble racetrack. Now, what happened here? We observed, if you observe, a marble thrown at any speed completes one revolution in time t. Meaning, if you take a marble and let's say you throw with speed v1, you will go in a circle. Let's say you take another marble and you throw with a higher speed v2, you'll go in a bigger circle. So that was the thing what was happening. They're not going in the same circles. If you have more speed, you'll go in a bigger circle, so distance will be more. So the question is, we need to find the equation of the track. So this curve, what is the equation of this curve? This does not happen for everything. It happens for a very specific curve. So that guy accidentally built actually in this curve, and that's the reason it took same time. So find the equation of the track. Or equation of the bowl. Is the question clear? So you made a bowl, smooth. When you throw a ball inside, it takes the same time. You throw slower or faster, it doesn't matter. नहीं आना. You have to prove it. You can't feel it. Do you get the answer? Did you feel it? Mm. When you're doing science, my feelings are dangerous. They are wrong most of the times. Don't feel it. Prove it. One thing I'll tell you, see, in physics, when this is not the first time, you will see this a lot of times. They'll give you something and they'll tell you find the equation of the curve, right? Whenever you hear this in physics, find the equation of something. Remember one thing: the only thing you know mathematically is the slope of a tangent is dy by dx. That is the only thing you know mathematically. So somehow you have to get that slope, right, using physics, and then you say that is dy by dx, and then you have to integrate. And this is not the first time. You have already seen this once. You know where? In differentiation. Do you guys remember this question? The light ray was hitting this, and it became 90. There we found the slope of the tangent, and then it's a dy by dx. This is the thing. So, and you will see this multiple times. You will again see this thing in elasticity. You will see this thing in fluid mechanics. You will see this thing in optics. Multiple places you will see this idea. They'll ask you find the equation of something. Whenever they ask you that, the main idea is that somehow you need to get that slope using physics in terms of y and x, and then you put dy by dx, and you're done. So let's see how this works. So let's say this particle is at x comma y. So this is going in a circle of radius x. That's your x coordinate. What are the forces acting on this? If you look at the forces acting on this, you have your mg, you have your centrifugal force m omega square x. So here, if I draw a tangent, this angle to be theta, this angle will be theta. We can clearly see the centrifugal force का component m omega square x sine theta cos theta will be equal to mg sine theta. So from here we get tan theta is equal to omega square x by g. So this is at some random point you have taken. So this would be m omega square x cos theta. This is mg sine theta. This is the slope of a tangent. So this black line is a tangent at that point. And we know slope of a tangent is nothing but dy by dx. Which is omega square x by g. This will be dy omega square by g x dx. Integrate this on both sides. Integral dy is equal to omega square by g x dx. 0 to x and 0 to y, and there we get your parabola. I square is equal to omega square by 2g. Interestingly, this is the shape, where you have seen. You've again seen this thing in calculus. This one, a paraboloid. So this is actually a paraboloid. So when you take a water in a glass of thing and if you spin it, the shape which you get is a paraboloid. And that shape is very special. In that, if you throw a ball, you are going to complete it in same time. Yeah. What is omega? Omega is time period, which is 2 pi by omega. Angular position by angular velocity. So from here we get omega 2 pi by t, and you can substitute it. Clear with this? There. That's your banking of roads. Take a break. Come back by 9:40. We'll continue from here. Any doubt so far? Ajo, and come back in 10 minutes. Yeah. I I did message in the WhatsApp and they had replied. Go on. Right, really. Right. Yeah, let's start off. The next thing, apparent gravity due to Earth's rotation. Now, this we will see again in gravitational force, but you can see it here also. So, because the Earth is rotating, if you take a person standing here at some angle, this angle theta is called colatitude angle. At equator, theta is 0 and poles mein theta is 90. Now, if you look at the forces here, now be careful, you are going in a circle about this circle. You're not going about the center of the Earth. So the centrifugal force will be away from this circle, m omega square, small r. This would be that small r, which is capital R cos theta, where capital R is the radius of the Earth. And how is your gravity acting? Gravity will act towards the center of the Earth, mg. So now when you look at the forces acting on this person, so what you're experiencing mg towards the Earth, there is a centrifugal force ka component m omega square small r cos theta. There is actually a tangential component also. So technically, we are not standing exactly toward the center of the Earth. We are slightly tilted. So if the Earth stops rotating tomorrow, you will see all the buildings a little tilted. You're not building it exactly toward the center. So and this would be a normal reaction. And so when we do this, we get n is equal to mg minus m omega square small r cos theta. And small r is g minus omega square capital R cos square theta. So this ends up with g apparent. So we think the gravity has decreased. G minus omega square r cos square theta. So be careful, it's a cos square. You get one cos theta because of that small r and one cos theta because of the component. At equator, theta will be 0. So at equator, you have a maximum loss of gravity. So that is the reason when these people are launching, rockets or spaceships, right? We prefer to launch it as close as possible to the equator. So that is the thing there. Now, one of the biggest problem, right, in space travel is this. So let's say if you're planning to send someone to Mars, it'll take a spaceship 2 years to reach Mars. 2 years just to go there. Coming back is a different story. One of the big issue we face, right? Yeah, there is a solar radiation, food, and all that stuff. The major problem is gravity. Human bodies are designed, to work in normal gravity. Right now, you're sitting there, even if you don't do any exercise, no gym, nothing, just sitting at your place, the gravity is pulling your body down. So the body maintains a certain muscle mass just to sustain. But when you put a person in a gravity-free space, there is no need for muscles to be there, and muscles are actually expensive, meaning they consume a lot of energy. So if you give a chance, the body will try to get rid of the muscles. You should see this, professional bodybuilders. They look really big, big muscles and everything. Look at them after 3 months after the competition gets over. They look pretty normal, actually. All that muscle is gone. So this is one of the big problem we have. And if you have seen Interstellar movie, right, they also have the same problem. The big problem they face is, first of all, how do we launch this whole thing into the space and how do we keep the people there? There's no gravity. So what do we do then? We cannot create gravity. People are still finding for a particle called graviton, which could explain gravity. Yeah, so far no luck. So what we have, So in the International Space Station, right, every day the astronauts do workout for 2 to 3 hours every day just to maintain their muscle mass. Even then, it is difficult. So the idea was this: we will create a big cylinder which rotates with omega. The first time I saw this was in Tom and Jerry. So in that, Tom, right, stays in a big cylinder kind of thing, and the Jerry is running around. I mean, when I was a kid, I didn't realize, but later on I realized. Yeah. So the idea was this: in this big cylinder, if you keep someone, there's no gravity there, but the normal reaction is in, and the centrifugal force is dragging you down. So that will be away from the center. And if we can make this equal to mg, your body can't tell the difference. This is down. The body can't tell the difference between actual gravity and the centrifugal force. So this is the speed with which you should rotate that cylinder. So on this big cylinder, if you construct cities or whatever, this is how the buildings will be. The buildings, so this is up. So toward the center of the cylinder is up and away from the center is down. So if someone is standing here, when you'll be at the top, I'll be at the bottom. Like me, again, what is up and what is down here. So you can say hi to me and I'll be like, hi. This is up and this is down. So this is how the buildings will be. They'll be all towards the center. That is how you can work it out. So if you're sending someone to Mars, you have to make sure in your spaceship there is a place, where there's a big cylinder which is rotating, and you keep people there. So except when you're not working, you make sure people are sitting in that cylinder and they're staying there. Their entire sleeping quarters and whatever should be there in that cylinder. So that's how it would work. So if you are constructing something to send people really far for years, you have to do this because there will be a major health issues. One big issue, right? Other thing you'll face is this. Forget about muscles. That is one. Second thing, your arteries and veins in the lower part of the body are thinner compared to the upper part of the body. So that is because you want to push the blood against the gravity. But once you go to gravity-free space, there is no one stopping the blood from going up. So all the blood will start accumulating in the head, and your brain will think you're producing a lot of red blood cells, and you actually become anemic. They stop producing RBC. You become deficient. So yeah, a lot of health issues you get. This is the scene from Interstellar. If you have seen this movie, I don't know whether you have seen this scene. So this is the climax there. This guy comes back and lands there. The volume is not great, but
Take it slow. The Rangers found you with only minutes left in your oxygen supply.
so some kids are playing baseball when they hit. See how it goes. Can you see the world, how it is? It is curved. And the ball goes there, and hits a building there. Look at how the buildings are. They're inverted. So they're actually inside a cylinder, which is rotating. You will see a better view.
Cooper Station. Well, the station isn't named after you, sir. It's named after your daughter. Here, they put us in some. Check.
Where is this? I think we'll see it now. Can you see the background, how it is? The whole thing is a cylinder. That's a big cylinder there. There, you can see this point of view. That's a big cylinder. So the light is coming from the center and the whole left and right are curved. And this is rotating there. You can see that curve, how it is. So when you're walking, you think you're walking flat only, but it's actually a curve. And this is what they do eventually. They do get away from the Earth, creating this big cylinder, and people stay inside. So story goes like that. So if you have seen the movie, you would have seen this scene. If you have not seen, then yeah, now you have seen it. So if you're sending people into the space, that's the way we can do it. Clear with this? That's your action due to gravity. So if you can rotate the Earth fast enough with this rotation, people at the equator will start flying off. Anyways, so that's about a little uniform circular motion. Next thing, non-uniform circular motion. What happens if the speed of the particle is not constant? So the speed of the particle is not constant. Now, if you remember a uniform circular motion, we had one component which is changing your direction. So the same thing will happen here. So the particle has centripetal acceleration, which changes the direction. So now we'll have two accelerations. Which is responsible for changing the direction. Or for making it go in a circle. Basically, this thing is changing your direction, which is v square by r. Now, what is happening? Since your speed is increasing, your v square by r is also increasing. So the centripetal acceleration won't be constant. And tangential acceleration, there is another one. This is responsible for changing the speed. Yeah, so think of like that. So think of that uniform circular motion, plus now you get an extra acceleration. It's not really that different. So A tangential will be dv tangential by dt. This will all look like your regular kinematics. The only thing, instead of going in a line, you're going in a circle. Or you can also write this thing as v dv by ds. So now, and remember, you're still going in a circular motion. You're still going in a circle, but with a changing speed. Now you'll have two accelerations. You have A centripetal and you have A tangential. So the resultant will be A net. If you take this angle to be theta, so we get A tangential is equal to R alpha. This is what we derived in the beginning. Alpha is your angular acceleration. S is your tangential distance. Or arc length, basically. And the net acceleration would be the resultant of both the accelerations, at square plus ac square. And the angle between them, tan theta, is given by A centripetal by A tangential. So concept-wise, there is really nothing more. That's it. Straightforward. If your speed is increasing, then your A centripetal also has to increase to keep it going in a circle. If you cannot do that, you will start skidding. So let me show you one example how they'll frame these questions. And so they will say something like this. Consider a vehicle going in a circle in a rough horizontal circle with acceleration A starting from rest. Right? So the tangential acceleration. R is the radius of the circle. Mu is the coefficient of friction. Find your speed. Is centripetal. A net. Frictional force at time t. So let me just show you one. So we got a circle, radius r. Initially your speed was 0, but you have an acceleration. A tangential is equal to a. Since a is constant, I can directly use the equation v is equal to u plus at. Done. I got speed v is equal to at. You want centripetal acceleration, which is v square by r. So this will be a square t square by r. Done. That's it. So straightforward. Things will just fall back to back once you know that thing. You want net acceleration? That would be root over a centripetal square plus a tangential square. So there are two accelerations now. Put it here, and then you end up with a power 4 t power 4 by r square plus a square. You want friction? The only one who provides the force here for you to accelerate is F is equal to ma. So think about it. So this friction, right, is actually providing both the centripetal and the tangential. So if I have to draw a picture for this is how it looks. Look at the accelerations. So initially when you're here, there is only a tangential. A centripetal is 0. And when you're somewhere here, this is your a tangential, this is your a centripetal. Your a centripetal is v square by r. So initially your speed is not increased much. So a net will be something like this. After some time, this is your a tangential. A centripetal must have become bigger. Speed has increased. Now a net will be something like this. If you leave some more time, the a tangential length will not change, but your a centripetal keeps becoming bigger and bigger. So your a net becomes like this. So if you see, your net acceleration is not towards the center, it's making some weird angle. And what about your friction? Initially, your friction will be in this direction. Your friction is also changing direction. So the friction ka one component is providing centripetal, friction ka one component is providing the tangential. Friction has to do both the work. There. So this is what is happening. So at any instant, if you try to get this angle theta, tan theta will be a centripetal by a tangential. So as v increases, a centripetal increases. That means friction has to keep increasing in order to satisfy this. The moment you can't do that, you will skid. So a net is provided by friction. Because it is a horizontal road, there is no banking, there's no one else. So they can ask you this question also. Find the time when it slips. So friction is m into a net, which should be less than equal to mu mg. So a net is nothing but a power 4 t power 4 by r square plus a square must be less than equal to mu g. So from here I'll get time must be less than equal to mu g u square g square minus a square into r square by a power 4 ka 1 by 4. Yeah, up to this time you're safe. Once you cross this time, the vehicle will skid. So what is the only new thing you learned? You'll get a speed v is equal to 80. Once you got the speed, a centripetal is same. A net will become a centripetal square plus a tangential square, and everything else will follow. So previously, when you're going in a circular motion uniform, friction used to be always towards the center because there is no A tangential. So friction has to provide only a centripetal. Now it will provide both. Is this clear, everyone? So tell me one thing. Let's say you're going on a curved road. You're going in a curved road and you're going with speed V. Rough road, okay? There's no banking. It's a rough horizontal road. You're going with speed V, which is exactly equal to mu RG. ठीक है? मतलब you're almost on the limit. Now, if you accelerate on this road, let's see, when you're going on this curved road, for some reason you accelerated it. Case 2, you applied brakes. In which case will you slip? You are going on a curved road at a critical speed. While you're going on that road, case 1, you accelerated the bike. Case 2, you applied the brakes. At the moment you did this, in which case will you slip? Will you slip when you accelerate or will you slip when you decelerate? Any answers? You got an answer, you can type here in the chat box. Decelerate, decelerate. Now let's think about this. When you're going with speed V, your friction is already maximum, right? And that is providing your centripetal acceleration. That means the friction does not have any bandwidth to do anything. Now see what happens. If you increase the speed, your speed will increase, means suddenly you'll get A tangential. If you apply the brakes, you will decelerate, means you'll get A tangential. You getting the problem there? Whether you decelerate or you accelerate, suddenly they'll come in A tangential. That means now the same friction has to provide A tangential square plus A centripetal square, which is greater than F max. The vehicle will slip in both the cases. But when you decelerate, you're lucky. What happens? You will slip, but the bike will immediately slow down. So A centripetal will decrease. Then friction will again catch up with that force and slipping stops. If you decelerate, you're definitely going to skid and fall down. If you accelerate, if you decelerate, you will skid for a moment, but then you'll get back to normal again. You must have felt it when you're going on a cycle and while taking a turn, you apply the brakes, you skid for a moment and then cycle again becomes normal. So you skid in both the cases. Let's see a question on this. Kinetic energy of a particle going in a circle of radius r. Is given by k is equal to ab into s square. K is the kinetic energy. S is your distance. B is some constant. M is the mass. Find the net acceleration as function of S. So the kinetic energy of a particle is given. And you can clearly see there, the kinetic energy is not constant. As you go more distance, you're getting faster and faster. So there is a tangential acceleration. Find the net acceleration as function of S. And this was I think, advanced PYQ. A pretty old one though. Let's see. Right, Ahana. Right, Prisha. Okay, Karthik, let's see. So kinetic energy is B square, which is equal to half mv square. So from here we get a v square, which is 2b square by m. So from here I get a centripetal, which is v square by r. There I got a centripetal. And then v square is equal to 2b by m square, differentiate on both sides. So when differentiate v square, we get 2v dv by ds, 2v by m, 2s. But if you remember, v dv by ds is nothing but a tangential. That would be 2bs by m. That's how you get a tangential directly by differentiating. Or you can do even dv by dt also. That also works. And then you're done. So a net will be, add both of them. So root over a centripetal square plus a tangential square. Substitute there, you get your answer. Easy. Next one. This is a good one. It's going to be a good paragraph question. Let's say we have a cylindrical rod. Which is going with alpha. On this cylindrical rod, you kept a ring. The distance from here to here is r. The friction is mu. Gravity is present. This rod is going with alpha, angular acceleration. Think of your fan. When you switch on your fan, it starts from 0 speed. Speed increases. It actually has an angular acceleration. This is a constant angular acceleration. So a ring of mass m is placed over a rough rotating cylindrical rod. So initially the rod is at rest. And has a constant acceleration. You must have, I don't know whether you did this thing in school or something. We used to take the duster, keep it on the top of the fan. And when you switch on that fan, for some time the duster stays there and then the duster flies and hits someone. Ever did that? Didn't do that. You guys are good people, right? Now the question, find the time when the ring slips. So if you keep something on top of your fan and if you switch it on, when the fan goes a little slow, it takes time before it slips. It doesn't slip immediately. The second question, if the ring is replaced by a square frame of same mass, find time when it slips. And then this is how the picture will become. I kept a square frame. Distance r, mass m, mu, everything same. Only the shape is different. Let's get these two questions. First, let's get the ring. Then we will talk about that square ka thing. What's the catch? So how will this even ring look like? I'll give you a little idea. See. Think about this. Suppose if it is not rotating. If rod is at rest, so this blue thing is the rod, the ring will look like this, everyone. So the ring will look like this. So two circles will touch at a single point. So this component will be your Ny and this will be the ring ka weight. So this vertical component will balance the weight. Suppose, second thing, if let's say the ring is rotating but neglect gravity. So if you have a bangle or something with you, if you take a pen and put it inside the bangle and if you try to move, if you look into my screen, right, this is how it looks. So if this is the ring and this is the thing, and when you put it here, can you see it touches at one point horizontally? So if there is no rotation, if there is a rotation but no gravity, then the ring will touch here horizontally at this point. This will give you an NX. And now if you have both of them, rotation and gravity, this is how it actually looks. It will be somewhere here at an angle. So the point is you'll be touching only at one single point. So the resultant will be N. But now there are two components. Now there is an Ny and there is an Nx. Since there is one point of contact, there will be one normal reaction and one friction. So be careful with that. So for every point in contact, there is one normal force and one friction force. One normal reaction and one friction. Yeah, great. That's the main idea about that ring and cylinder and everything. Just think about it. Instead of a cylindrical rod, if I had given a square rod, meaning if the rod was like this. Now when you put a ring on this, won't it be touching something like this? It will be touching at 2 points then. So then you'll have two normal reactions and two frictions. So shapes do matter. So now let's draw the free body diagram. we are doing for the first case. So what are all the forces? Your own weight mg, n ka component ny. There is a component nx. So this nx is actually tangential. Then there is one friction this way. There is one centrifugal force this way. And there is also this acceleration A tangential. This is R alpha. These are all the forces that you have. So what is Ny? Mg. What is Nx doing? Nx is providing the tangential acceleration, m into A tangential, which is mr alpha. What is omega? Omega is equal to alpha t. So and we use this formula. Omega final is equal to omega initial plus alpha t. So this is what is happening. As time passes, you're going faster and faster. Centrifugal force is increasing. Friction is the only guy who can balance the centrifugal force. So F is m omega square r. This must be less than equal to mu into n. So omega will be alpha t whole square. But what is n? N will be root over nx square plus ny square. That was the thing. That n will have two components. You have to take the net normal reaction. Yeah, I think you're done. Then you can substitute here m alpha square times square r must be less than equal to mu. Nx is, you can take out that m common, r square alpha square, and y is g square. M gets cancelled, we get time will be less than equal to mu root over r square alpha square plus g square y alpha square r ka whole power half. Check, that's your answer. So until this time, there'll be no slipping. So that was the main idea there. So the ring will be at an angle, and that will generate two normal reactions, and each one has a role to play. And when you take F is equal to mu n, you should take that net normal reaction. Everyone clear with the concept? How does that affect the problem if it is a square ring? Can you do that? Try, I'll give you a minute or two. Idea is the same thing. What happens if you have a square frame? Clear, na, Sumana? Any doubt so far, Rohit? Karthik? Clear? Ananya? Ahana? Manav? Give it a try. Try it for a square frame. What changes with a square frame? So if you draw the free body diagram, this is how it looks. So the circle will be touching it. Like this at two places. So story is still the same. This will be ny, this will be nx. But this time the difference would be, there'll be two frictions. So now when you draw the free body diagram, we have ny, we have nx, and just write somewhere here. Everything will look same. But this time there'll be two frictions, fx, fy. This is mg. So ny is mg. So it's like this, a plus b is greater than root over a square plus b square. You actually get more friction here. Nx is providing the A tangential. mr alpha. So we get fx plus fy is equal to m omega square r. This will be mu times nx plus ny. In the previous one, this is mu into nx square plus ny square ka root. mr alpha plus mg and omega will be alpha t whole square into r. Yeah, this is a better one. So mu into r alpha plus g by alpha square r whole power of. So which one is going to slip first, the square or the circle? Who has more friction? The square has more friction, right? So the circle will slip first. So the shape actually affects the answer. So this is the condition for no slipping. Clear with this? That way. Last one for the day. We got a circular track like this. Top view. So this is a rough wall. But the ground is smooth. Smooth floor. So we have a block here of mass m which enters this circle. This is the radius r. So this block enters with speed u, and when it leaves this circular path, it comes out with speed v. So what's actually happening here? Look at this picture here. The block is entering with speed u, and as this block is going on the curve, this is what you will notice. So finally the block comes out with v. So when you're sliding on the wall, right, there is a friction here. The floor is smooth, so there is no friction on the floor, but there's a friction on the wall. Because of this friction on the wall, you actually slow down, so you get a tangential friction. So you basically enter into the curve with a speed v, then you slide on the wall, which is rough, and then your speed decreases, and then you come out with v. So block enters a circular rough curve of radius r. That angle is theta. It's not a complete circle also. It enters with speed v. It slides on the rough wall. Because of that, your speed will decrease. As shown. It enters with speed v, speed u. Find the speed when it comes out. Is the picture clear, everyone? So when you're going in a straight line, there is no problem. Something like this happened, I think 1 or 2 years back, or I don't remember. It happened in F1 car race or something. So what that guy did, he took his car and he just smashed it to the wall and he started accelerating at full speed. There is a thing like that, and he won the race, I guess. And after that, it was banned actually. You're not supposed to put your car to the wall and accelerate. I don't remember that incident. I think it happened, don't know when. There was someone who did that. Because when you're normally going on a road, you increase, right? There's a chance you slip. But if you touch the wall and you just put the thing at full speed, you're not going to go away from the track. It's pretty dangerous. The parts and pieces can fly and hit the spectators. So once you enter, you start grazing on the wall. Start with a free body diagram. See which forces are there. If you think about this thing, when you're sliding on the wall, the centrifugal force is pushing you against the wall. That is providing the normal reaction. And the normal reaction is generating the, what do you call, the friction. So then you slow down. But if you slow down, your centrifugal force decreases. If your centrifugal force decreases, normal decreases, N decreases, friction decreases. So if friction decreases, then your rate of acceleration will decrease. If your acceleration decreases, speed decreases. So if you see, this function is killing itself. The slower you go, the lesser the friction you're getting. These are kind of decay functions. So if you draw your block here, this is how the picture will look like. Your weight mg, your normal reaction, your friction. There are two normal reactions. This is the N floor, which actually we are not interested because there's no friction on the ground. This is N wall. And there will be a centrifugal force and V square by R. This is also F wall. So F wall is mu into N wall, which is mu into mv square by R. So F wall is creating your m into A tangential. We get A tangential is mu v square by R. And if you see, it is not constant. It is depending on your speed. A tangential can be written as minus v dv by ds. Minus because it's decelerating. is equal to mu v square by r. When v cancels off, you end up with a dv by v is equal to mu ds by r. Integrate on both sides. Mu by r, you can write ds as r d theta. This will go from u to v and this will go from 0 to theta. That will be ln v by u is equal to minus mu by mu theta. V at v is equal to u into e power minus mu theta. That's an exponential thing. Yeah, this thing will never stop actually. That's a generally that happens. Like whenever the function is killing itself, it is generally an exponential decay functions. Clear with this? That's a little bit on non-uniform circular motion. So next class when we catch up on Wednesday, we'll continue from here. We're going to do something called radius of curvature. Then we will see problems like that Coriolis force and all that stuff. 1 or 2 examples we'll see on that also. So mostly we should be able to finish all this chapter in the next class. And let's see if time permits. Maybe we'll start off with work per energy or whatever it is. But yeah, we have done almost 26 questions. I'll send you a sheet also on this. You can start working on this. So yeah, with that, we'll wrap up for the day. I'll see you guys on Wednesday, same time. So any doubts, anything else, stay back and ask, or feel free to leave.